So we're going to continue with our discussion of routing protocols and talk about OSPF. Now you'll recall from our overview of routing protocols that OSPF is the open shortest path first protocol. It is a link state protocol that's supported on just about every piece of modern networking equipment out there. It's not Cisco proprietary. In fact, there's hardly a networking device out there that doesn't support OSPF. And as a result, it is probably the most widely used interior routing protocol that you'll see, if you're not working on an all-Cisco network where they'll probably be using EIGRP. Now, obviously, we're going to get a little more in-depth than just this overview, but for the purposes of this overview, we're going to break down OSPF operation into three general categories. The first is neighbor relationships. What are OSPF neighbors? What do they do? How do they work? The next is LSDB exchange, or the Link State Database Exchange, and that is where a pair of OSPF neighbors exchange link state advertisements to build a full copy of the network topology in their routing tables. And the last is the route calculation. And again, we touched on this in our overview of routing protocols, but we'll get a little more in depth with it in this overview and in some of the follow-on videos. So first, let's talk about neighbor relationships. Like EIGRP, OSPF maintains a neighbor database that is used to determine when routes and routers go down and react accordingly. Now, we'll get a little more in depth with how this happens in later videos. But for now, just know that OSPF can detect when its neighbors go down and can modify its local link state database accordingly. Now, when a router running OSPF comes up, it immediately starts sending hello packets to a multicast address of 224.0.0.5. Every router that runs OSPF listens on this multicast address, and by default, these hello packets are sent every 10 seconds. Now, among other things, every router that runs OSPF listens to that multicast address for new neighbors, and that's how it also learns about link state changes and so on. But for the purposes of our discussion, it's for learning about new neighbors. Now, when an OSPF router detects a new neighbor coming up, it looks at some of the key parameters that are in that hello packet to determine whether or not we can actually be neighbors and start exchanging routes. And if those parameters match, then the routers start the link state database exchange process. Speaking of which, the next thing we'll talk about is the link state database exchange process. Funny how that works, isn't it? Every router knows about every other router on the network, but not always via direct link state advertisement exchange. Now, obviously, we've talked about the way that OSPF maintains a topology database, and obviously for this topology database to be valid, OSPF has to know about every router out there. But just because two OSPF routers are neighbors doesn't necessarily mean that they'll actually exchange routes directly with one another. Whether or not a router directly exchanges link state advertisements with its neighbor is determined by the network type. Now, obviously, on a point-to-point network, there's only 2 points on that network, hence the term point-to-point, and the LSAs are exchanged directly between the two routers. Now, you'll see this most commonly on serial links, but also if you have an MPLS connection, you can tell the OSPF routers on both ends of that connection that, hey, this is a point-to-point network, even though it doesn't look like one, and so you just exchange routes directly. On a broadcast network, i.e. an Ethernet segment, OSPF elects a designated router and a backup designated router to manage the link state advertisements for the subnet. And the role of the designated router and the backup designated router is to receive the LSAs from each of the routers on that subnet, process them, and then forward them along to all of the other routers. And you might think, well, why do we do that? Well, if you think about a situation where you have 5 routers on the same subnet, if every router pairs with every other router, you'll have several dozen pairs of neighbor relationships between routers on the same subnet. For every router that has a neighbor relationship and is exchanging LSAs, you're going to increase the traffic on that segment exponentially. In a designated router scenario, if I have a link state change, I tell one router, that one router tells 4 other routers, and so that way you only have 5 copies of the LSA going across the network instead of 70 or 80, because I'm going to tell 5 routers, those 5 routers are going to tell all of their neighbors are going to tell all of their neighbors, and so on and so forth. It just snowballs out of control. We'll examine this when we get into the lab. I have a segment set up that is an Ethernet segment with multiple OSPF routers on it, and you'll see how the DR and the BDR helps maintain stability on that segment. Finally, we'll talk about route calculation. Once every router has all the LSAs, it can build a complete map of the network in the router's memory, and that's the magic sauce in link state routing protocol. OSPF uses the Dijkstra SPF algorithm to determine the best path between two subnets. The OSPF metric uses path cost as basically the sum of the bandwidth between any two subnets as its metric. Each interface speed has a specific cost associated with it. Cisco uses 10 to the 8th power divided by the interface bandwidth. And as you can see by that basic back-of-the-envelope math calculation, higher bandwidth speeds result in lower metric scores. Like everything else, lower is always better. Once the best route is calculated, that best route is installed in the routing table, but kind of like EIGRP, OSPF knows that there are other paths to get to the same network, and so if that main path fails, it can recalculate the link state database and start using the other path immediately because it knows about the entire network topology. It doesn't have to go out and search for a better route. If there are multiple equal cost routes to a destination network, they are all installed in the routing table. So OSPF gives you the ability to do equal cost load balancing across multiple links in your network. And that concludes our overview of OSPF.